Hello, we are continuing with the quantum mechanics of hydrogen atom, and today we'll be discussing about the electron probability density, which tells us about the probability of finding the electrons within the atom. Now, the quantum mechanical description of the energy states of one electron atom is similar in many respects to the old quantum theory that were provided by Bohr and later on by Sommerfeld. Yet there are striking differences regarding the motion of the electron within the atom. Now, quantum mechanically, the electrons cannot be considered as moving around the nucleus in definite orbits. We can consider only the relative probability of finding the electron in volume elements at various locations. Let's see what we have at hand. Now, the electron wave function that was provided, that is psi NLML, that depended on r, theta, and phi, that is equal to RNL, which is a function of the radial, the position, and then we had theta, the capital theta, LML, function of the theta variable, and then we had the azimuthal function, which is phi, capital Phi, which is dependent on this phi. Now, these three, they describe how psi varies with r, theta, and phi respectively. And the three-dimensional electron probability can be given as psi squared, and that is equal to r squared, theta squared, and phi squared. Now, this psi squared is obviously psi, and it's multiplied to its conjugate. Now, the azimuthal probability density, that is phi squared, that is simply equal to phi with its conjugate, the product of phi with its conjugate. Now, as we know, we had obtained a solution. The solution was of the form a exponential of I times of ml times of phi, and its conjugate will be a times of e raised to the power minus I ml times of phi, and multiplying both of them we'll just get a squared. Now, a squared is just a constant term, which means that the probability psi square does not depend on phi, because it's a constant quantity, and it will be symmetrical. It will be, or it is symmetrical about the z-axis, because that's the axis that we have considered for the azimuthal angle. Now, it will be symmetrical about the z-axis regardless of the quantum state of the electron. Now, if we are to consider the dependence of psi square on r square and theta squared, then we can obtain those probabilities. We'll be providing a graphical analysis for that. Let me draw the graphs first, and then we'll be discussing it further. So here are the three plots. We consider the probability, the radial probability with respect to the position from the nucleus, and we consider it in the 1s, 2s, and 2p states. Now, first up, we are considering the probability or the dependence of psi square on r square. Now, we define it as the radial probability density, and that is PR. So PR here is the radial probability density, and what it tells us is that it is PRDR. If we are to take that, then that will be the probability of finding the electron within the distance between r and r plus dr, that is from the nucleus, which means we'll be considering a shell which is of thickness r and r plus dr. So the volume in that case is given by 4 pi r square dr. So that is the volume of that enclosure between the spheres of radius r and r plus dr. Now the graph of PR versus R has been provided for 1s, 2s and 2p, as I said earlier, and this is for hydrogen atoms z is equal to 1. We see that the states 1s and 2p, the maxima of the curves are exactly at 4a0. So for 1s we have at a0 nearly, and here we have at 4a0 down below, the last one. Whereas in case which are exactly in agreement with the Bohr's radius, that is for the hydrogen atom we had the corresponding values of n being equal to 1, and here n is equal to 2, so we have those values of the Bohr radius. They are in complete agreement. For the state 2s, however, the main maximum is little deviated from 4a0, so this is not exactly at 4a0, and it also has a weaker maximum over here. So thus, whereas the electron is most likely to be found on locations of the Bohr's orbit, it has finite probability of also being found elsewhere as well, which is suggested by that small peak that we see in the 2s state. Now the average distance of the electron from the nucleus can be given as let us say that is r barred, and that is from 0 to infinity r pr in that region dr. And on evaluating this, what we get the value to be equal to is that r barred is given by this, where r bar is equal to n square times of a0 over z, and that multiplied to whole of that bracketed term 1 plus half times of 1 minus L times of L plus 1 divided by n square. A0 here is the smallest Bohr orbit. Now this is somewhat similar to the case of Bohr's Sommerfeld elliptic orbit, if we are replacing that L times of L plus 1 over there in the numerator by the value k that was obtained in the Bohr's Sommerfeld theory. Now the value of the average distance of the electron from the nucleus is obtained or is evaluated to be 1.5 times of a0, 6 times of a0, 5 times of a0 in case of all the three states, that is 1s, 2s and 2p for the hydrogen atom. These values are somewhat larger than the corresponding values of R for maximum radial probability density. Now this is because of the asymmetrical nature of the probability density curve about its maximum, which is given in those figures. So that's as you can see, let me take you back to those figures. As you can see, those plots are asymmetrical about the maximum radial probability density. So from that we get this deviation, this very little deviation in those values of R barred in those states. We also see that except for n is equal to 1, the probability of finding the electron near the nucleus is smaller than that at far away distances. This is in agreement with the Sommerfeld elliptical orbits, in which the electron moves faster when passing near the nucleus than when far away from it. Now we finally consider the directional dependence, that is psi square on theta squared, and we'll have a set of figures to represent that as well. So here are the set of diagrams for the S state, for the P state and for the D state, where we have the values of L to be equal to 0. So this is L is equal to 0, L is equal to 1, and then we have L is equal to 2 over here in each of these states. And so we are obtaining these polar diagrams for theta squared, and let me change the ink. So at r is equal to 0, that is with respect to origin, and we consider the z-axis in each case, giving us the z-axis is taken along the direction from which the angle theta is being measured, as you can see in the diagrams. The angular probability density theta squared is a constant for the S state, and it comes out to be equal to half, and that results in that is for L is equal to 0, and that being a constant, you have the probability density psi square is spherically symmetrical about the nucleus, so it is independent of, it was independent of phi. Now it is also independent of theta because the value comes out to be a constant one. For the other states, however, where the theta square varies with theta and takes on the largest values in definite directions. In a given state other than the S state, the concentration of the probability density shifts from the z-axis to the plane perpendicular to the z-axis as the absolute value of ml increases from 0 to 1. So here you have the value of ml to be 0, here you have the value of ml to be 1. So as you can see, there has been a shift. It has shifted to a plane which is perpendicular to the z-axis. So here was the z-axis over here, and the z-axis is still there, it does not change. However, now the probability, you can see those dumbbells that were vertical, now they are horizontal. Those dumbbells represent the probability of finding the electron in those at those points. These are more or less in the form of electron clouds, if you have heard about it. When you may be I'll provide you with the figures, uh, probably try to provide you in this video. I'll have to draw it, uh, so let's see if I can provide that. So the three-dimensional characteristics of character of the psi square for a few states of one electron atom can be shown in this form. Actually, these are in the form of electron clouds. So I'm trying it over here. So if I consider this spherically symmetrical case, what I mean by the term electron cloud is that we have the probability of finding the electrons in these points over here. They will be in the form of clouds. These are not the electrons because there is a single electron, but these points give us the probability where we can find those electrons. This is in the 1s state. Now in the case of 2s state, however, is a bit of a change. Now this is the maximum probability. This white portion that you see has the maximum probability. Now this is in the 1s state. In the 2s state, however, we have the case where we have one probability over here, and the rest of the probability is at a small distance away from it. We have a rim of sorts, or we can say a shell in this case. So the shaded portion here is the portion that we are going to expect the electrons to be in. We will be also expecting the electrons to be in this region, but there's a blank space in between. Now this is the state in this 2s state. It is spherically symmetrical for sure, but there is a spherical nodal shell between the inner sphere and the outer spherical shell. The nodal surfaces are a consequence of the fact that the wave functions for a bound particle must be standing waves with fixed nodes. So, so we have this kind of a figure. So in all the S states, the maximum probability is near the origin. So that's that white portion, that white patch that you see near the center, that is with the maximum probability. And those white dots that you see away, they're just like sprinkled white dots. In this case, I have made them blue dots. So they will tell you that the probability gradually decreases. And then also I have explained about the nodal surfaces, which are a consequence of the bound particle being in the form of standing waves with fixed nodes. And then we have the probability of finding in the p states, which shows the dependence on theta, and that has been clearly provided in these diagrams that I have provided to you. Now, what we conclude from this, that there are many points at which the quantum mechanical theory of one electron atom corresponds quite closely to the old quantum theory of the given by Bohr and Sommerfeld. For example, both the theories result in quantization of the total energy of atom, and they give the same energy values. Similarly, both agree on the quantization of the angular momentum as well. But in case of the old theory, that is in the Bohr-Sommerfeld theory, the numbers were introduced as postulates. They were included as postulates. While in quantum mechanics, they appear automatically when we are trying to find acceptable solutions to the wave equations. Now, as far as the actual motion of the electron within the atom is concerned, the two theories differ appreciably, as you can see over here. In old quantum theory, the electron traces fixed elliptic orbits whose size, shape, and orientation are determined by quantization rules. In quantum mechanics, on the other hand, the electron cannot be allotted definite orbits. It has only relative probabilities of being found in those various locations. The probability is, of course, the maximum at the locations that have been indicated by Bohr-Sommerfeld orbits, and but also we find the case that they are not really zero elsewhere. So there is a probability of finding them, just like we had obtained these cases where they were deviating slightly, and also in the 2s state in the previous graphical analysis that we found over there, there was a short peak in the 2s state. So that really told us that uh, the probability of finding those electrons is not exactly zero at other points. They can be found at other points as well. And hence, in quantum mechanics, the electron is actually smeared over the whole space, just like an electron cloud. So all these things that you are observing over here, they are nothing but electron clouds, which are providing the probability of finding the electron at those points. There are not that many electrons. It's a single electron atom, but there's a probability which leads us to trace those points, and they provide a cloudy image, and that is why they are called as electron clouds. So this is clearly consequence of the wave nature of electron. Uh, as we will be seeing, that the quantum mechanical theory has been very successful in explaining the spectra of multi-electron atoms, and also the relative intensity of the spectral lines as well. So that's what we were to discuss in this video. Hope you get a clear picture of where the electron stands within a one electron atom. We'll be trying more such concepts in the upcoming videos. Till then, thank you for watching.